Hi everyone, I'm Alex, and today I'm going to present our work Freetures. This work is a collaboration between the Microsoft Mixed Reality and AI Lab in Zurich and ETH Zurich. In this presentation, we're going to be discussing 3D reconstruction. Here, we see a 3D reconstruction of the Deutsches Museum in Berlin. You can see the path taken by the observer, here shown in red. Under the hood, this large-scale reconstruction is formed by composing a collection of reconstructed fragments. Here, each fragment is shown in a different color. Here, we see each of the reconstructed fragments, or submaps, laid out on a grid. Having built such a reconstruction, it is often necessary to perform localization against the reconstructed map. In this context, localization amounts to the following. If our agent observes a piece of geometry, we would like to know if there is significant overlap between this new observation and one of our submaps. Let's discuss the standard approach to this problem in a simplified 2D environment. The agent wants to know where it is in the map. It first picks some interest points on the surrounding surfaces and summarizes its view as a vector of these interest points. We then use this vector to index into a database of previous views. All going well, the database responds with the agent's location. In this work, we advocate the use of a distance function representation of the environment displayed here on the right. I want to give some intuition as to why we think that this might be a good idea. If we consider one of our surface interest points from the previous slide, this point has an equivalent in the distance function representation. However, there are some points like this one which appear both interesting and have no equivalent in the surface map. The idea of this work is that by utilizing points like this one, located in free space, that we improve localization performance. So this is what the distance function looks like for one of the submaps from the Deutsches Museum reconstruction. Distance here is shown in color. We detect interest points at areas of high distance function curvature. Here, we visualize the curvature magnitude as a colored point cloud. The red spheres indicate the locations of detected interest points. Here you can see in purple a collection of gradient vectors of the distance function which surround a single interest point from the previous slide. Our descriptor takes the form of a gradient orientation histogram. This animation shows the process of compressing these vectors into our descriptor. Given interest points in their descriptors, we are able to register submap pairs. This animation shows a successful match between the submap at the start and a submap at the end of the Deutsches Museum trajectory. Each submap in this animation is shown through its distance function curvature. We tested our system in 4 environments: in 2D and 3D building scale LiDAR datasets, as well as a room scale dataset reconstructed using a depth camera. Across each of these widely varied environments, and with respect to strong baselines, we found significant performance benefits of using our own method. Furthermore, we showed that these performance gains were directly attributable to our use of free space. Finally, we demonstrated our approach on our hexacopter MAV. Here, we show reconstructions from 2 flights through a search and rescue training ground. Using the proposed approach, we register the top map against the bottom and produce a consistent combined reconstruction. I'm now happy to take questions.